Okay, folks, we can get going. Are there any questions before I get started on anything? Any questions or concerns about the progress reports that folks are turning in this week? Yeah? You'll submit them on Canvas. There should be an assignment posted at this point. And I'll just clarify, the notion with these progress reports is not that they should really take you much time at all to complete. It's just a brief summary of stuff you did this week, stuff you plan to do next week, hours worked this week, and so on. And I am interested in reading them, though, perhaps obviously, because I'm in the lab all the time, there's generally not anything in those documents that's new information to me. But it's really, experience shows that it's mostly to the benefit of students to take a moment every week to sit down and plan for the coming week what their tests are going to be. So it's worth taking seriously, I suppose. It's just what I'm encouraging. Any other questions from anyone? I got a question on Canvas about how folks should retrieve the components that they have put in purchase request forms for and that I've ordered. That stuff has started rolling in. I have it in my office at the moment. My plan is just to bring it to lab sections and drop by lab, and we'll see if any of that stuff's yours. Okay. Anything else from anyone else? Okay, so I'll just remind you that now that we're in final project season, we're on to this sort of special topics collection of lectures. So we're no longer talking about stuff that is of immediate relevance to lab assignments, but is instead of general relevance to people that are interested in microcontrollers and stuff that may perhaps be of use to some of your final projects. What I wanted to talk about today, one of the awesome benefits of using a essentially wholly open sourced microcontroller in a class like this is that it gives us access to software that in many other microcontrollers might be proprietary and hard to get access to. For example, the Git repo associated with the RP2040 contains all of the boot code, which is amazing. So we can go through it and learn from it. And so my plan for today is to go through and try to talk about all of the stuff that happens before main in your program actually gets called. I'm doing this for a couple of reasons. One, I think it's kind of interesting. And the second reason is that a couple of groups are doing projects for which it would perhaps be a stretch goal to implement a custom bootloader. So let me just remind you for context, a bootloader is the program that allows for you to load other programs onto the microcontroller. The RP2040, of course, like all other microcontrollers, ships with a baked-in bootloader so that we can actually program it when it arrives. In the event that you wanted to change the mechanism by which a program actually got onto the microcontroller, what you would be doing is writing your own custom bootloader. A great way to start that process is to learn about how the existing bootloader works, and then we can sort of modify it. And so my plan is to talk today, sort of in short, I'm going to be kind of abridging this story, but I want to talk today about how the existing bootloader works, and then in a subsequent lecture, I'm going to talk about a custom bootloader based on this one that allows for the user to put new programs onto the RP2040 through a serial interface, as opposed to the USB interface, or as opposed to the bootloader. Okay. Any questions about that stuff before I get going? Okay, and the document that I'm presenting from is one that's linked up on the course homepage. This is not really, I did not modify this to improve its sort of presentability. There's more text here than would probably make sense for a lecture. But I'm going to be bouncing out to code and to other resources, so I'm largely just using this document to guide our conversation. So that's just why this looks a little bit like it's a little bit more verbose than it otherwise would be. So what happens when you power on the microcontroller is the following. Perhaps as stands to reason, the first events that occur are fully hardware controlled. So that is to say, when you first turn this system on, the first stuff that happens is stuff that is caused to happen by hardware, not by software, because there's no software running yet. And in particular, what happens is you turn the system on, and the RP2040 will check whether or not that run pin is high. For as long as run is not high, that is to say, if run is grounded, the system is held in reset. Some of you have programmed the little boot select via double reset button onto your breadboards. And you may remember that that button stretches between the run pin and ground. What this is telling us is that that run pin, when we push that button and ground run, we're putting the system into reset. And when we first apply power to the system, it checks that pin to see whether or not that pin is high. And only in the event that that pin is high does do the rest of these events occur. Okay, so it checked the run pin. The next thing that happens is the system will stall until the internal voltage regulator stabilizes. We're applying some voltage, we're waiting for that voltage to stabilize, and then a power on state machine begins. This state machine is responsible for powering on the bare minimum number of peripherals that are required for the rest of this boot process in the correct order. Perhaps it stands to reason that the performance of some of these peripherals rely upon others of these peripherals having already booted up and being stable. And so this power on state machine powers on a subset of all of the peripherals in a specific order so that we can go through the rest of the process. So in particular, it starts the ring oscillator first of all. The ring oscillator is worth knowing about for your final projects in any case. The ring oscillator is a clock source on the RP2040 that is composed just of a ring of inverters. That implies a couple of things. One of the things that it implies is this ring oscillator requires no external hardware to run. It's fully internal. It's just a little ring of inverters. That makes it much lower power than your other clock sources. Okay, it's lower, for instance, than your external crystal clock oscillator. It also starts up faster. To start up the rest of the system takes a little bit over a millisecond, the other clock systems. This ring oscillator boots up right away. And it's lower power. But there is, of course, a trade-off. And the trade-off associated with the ring oscillator is its frequency is not constant, like your other clock sources. Your other clock sources, of course, come from your crystal oscillator, which go into a phase-locked loop, which give you a nice, stable frequency. This ring oscillator, its frequency is a function of process, voltage, and temperature. So what that implies is the speed with which this ring oscillator clock is ticking depends upon the code that's being executed. It depends upon the temperature of the chip, and it depends upon the voltage that you're applying to the chip. That implies, for instance, that you might be running some program off the ring oscillator. It's running at some speed, and then you cool the system down and it will speed up. You increase the voltage that you apply to it and the system will speed up. For some applications, that's great to know about because it means that you can run your system off of a lower power clock at the cost of stability of the frequency of that clock, but there are a lot of applications for which that doesn't matter. There are a lot of applications for which that does matter a lot. This in particular would make it really hard to interface with external stuff that requires a stable clock input. The VGA screens, for instance. Right? In order to drive those VGA screens, we need to update the pixels at exactly 25 megahertz. It'd be very hard to make guarantees like that with this ring oscillator. Right? But if you're just running some internal thing, then that's perhaps worth knowing about, particularly for really low power applications. But okay, the first thing that happens is this thing turns on because that's the clock that we are going to use to do the rest of the boot process, because we have not yet actually booted up the crystal oscillator or turned on or allowed to stabilize any of the phase lock loops, right? So we're going to be doing our boot process off this ring oscillator. The crystal oscillator is then reset, but we don't start it yet, actually. That actually occurs at the end of the boot sequence, but we do reset it. We bring out of reset the reference clock and the system clock, and we use the ring oscillator with no divider to run the reference clock. So that is all just to say that we are going to be running the system off of the ring oscillator for this boot process. We put all non-critical peripherals into reset. We check whether there's an invalid program in the flash. We bring some stuff that we will require for the rest of the boot process out of reset. In particular, we're bringing the execute in place memory out of reset, ROM and SRAM out of reset, the bus fabric out of reset. And then we begin executing code in the boot ROM. And I'll just remind you that this is a fully automated process, right? Our code doesn't control any of this. This all just happens when we turn things on. The other thing that just happens when we turn things on is what I'm about to describe, which is the tasks accomplished by the Bootrom. The Bootrom, I'll just remind you, let me just pull up a data sheet here. Oops, cancel. If we pull up a data sheet, let me just show you that diagram we've looked at a whole bunch of times this semester. This one here. Let me just remind you that the Bootrom, which lives here and connects immediately to the bus fabric, this is internal. This is a part of the chip. It's on chip, that is to say. Just remind you that on the RP2040, our flash memory, in which we're actually storing our program code, is external, lives out here someplace, and we communicate with that via this QSPI interface. This is a high-speed SPI channel that interfaces with our execute-in-place cache system here, right? The ROM that I'm about to describe is on chip. Now, I'm going to abridge the story of the ROM a little bit, but in short, what the ROM is responsible for doing is figuring out whether or not there does actually exist a valid program in flash memory, and furthermore, figuring out which of the handful of compatible flash chips with which I might be communicating am I actually communicating. It doesn't know when it boots up, right? Because it's storing its program heading out here in flash memory. There's a bunch of different chips that it could be using. It doesn't know when it turns on which one it is using. And so that's one of the things that it has to figure out. So what it'll do in particular, let's take a look. Let's see. What it does in particular is the following. And we can look at this in code. Let me just summarize it here first of all. It's a dual core system, right? You use both those cores in Lab 2. So both of the cores will enter the Bootrom. The first thing that each core does is read that CPU ID register that you may remember us talking about when we were looking at the SIO, the single cycle IO block. This is a register that each core can read, and if core 0 reads that register, it will find a 0 there. If core 1 reads that register, it will find a 1 there. So it's a way for each core to learn its own identity. The first thing that each core does is look up its identity and ask, am I core 0 or am I core 1? In the event, so for core 1 stops there and just goes to sleep. On this system, as it turns out, core 0 is responsible for booting up and turning on core 1 in the event that the programmer asks it to. But it's core 0 that actually goes through the rest of this process. It then goes through and checks whether some debugger flags have been set. It then, interestingly, this is perhaps worth knowing, it checks whether the watchdog peripheral has set a boot to SRAM flag, in which case it immediately sets the stack pointer and jumps to the entry point specified by this watchdog boot to SRAM flag. What this is implying is if you go read the chapter associated with the watchdog peripheral on the RP2040, what you can actually specify is that in the event of a watchdog reset, you can have it boot to some other program that lives in flash memory. It's kind of interesting. Okay, in the event that there is no boot to watchdog flag set, it waits for a little bit, pulls up the flash memory chip select line. It reads the flash memory, right, configuring a few pads in order to do so. And then it starts looking to see if there exists a valid program in flash. How does it tell if there's a valid program in flash? What it does is it goes through, loads the first 256 bytes from flash memory into RAM. This is why RAM was one of the peripherals that we turned on in that hardware-controlled part of this process. Reads that into RAM and computes a checksum from it. In the event that it finds a valid checksum, that is to say it computes the checksum on those 256 bytes, it knows the checksum associated with a valid program. We'll talk about how it knows that in just a moment, right? But it's looking for a particular checksum. In the event that it finds it, it enters the second stage part of this flash boot process that I'll talk about. In the event that it doesn't, it changes the SPI configuration and tries again. Remember from our SPI lecture that there's a number of different modes that an SPI channel can be in, right? We can change the clock phase of an SPI channel, and we can change the clock polarity of an SPI channel. As it turns out, these various external flash chips with which we might be interfacing, they use different SPI modes. This boot process does not know which chip lives there, so it doesn't know which mode to configure, so it just tries all of them. So it tries the first one, checks for a valid checksum. In the event that it finds one, great, it'll go do what I'm about to describe, the next part of this process. In the event that it doesn't, it just keeps checking until it goes through all of them. If it goes through every SPI mode and it does not find a valid program at the start of flash memory, then it goes through the rest of this process in which it enters USB device mode boot up. It basically goes into boot select mode. It says, I didn't find a valid program, so I'm just going to wait for the user to give me one. So this is why, just by the way, if any of you have asked me for a new RP2040 and I got you one out of the box, fresh from the store, there is no program on there, you may have noticed, if you were paying particularly close attention, that when you just plugged that in, without even holding the boot select button, it went automatically to USB boot mode. The reason that it did that is it went through this process. It found that there did not exist a valid program there, and so it just went straight into boot select mode. Yeah? It does. It affects which part of this process? I can't remember. But there's a check someplace in here to see whether that pin is pressed, in which case it jumps straight to USB boot mode. Okay. Questions about that? So remember, what we just talked through, this whole process here, which, by the way, if you are interested in looking at, this process is described. You can go onto the GitHub and find the Bootrom and go through this whole process. It's a great refresher, incidentally, in ARM assembly, which I think many of you would have been exposed to in embedded systems, right? So this whole boot process is written in ARM assembly, but you can go look at it there. I want to complete this story, which is why I'm kind of brushing past that. It's not because it's not interesting. Okay, so let's suppose that we have found a valid checksum. That means we're going to enter boot stage 2. And that's the next thing that I want to talk about. Boot stage 2, in contrast to the boot ROM, remember the boot ROM lives on chip because it has to, right? Boot stage 2 does not live on chip. Boot stage 2, the second stage of the bootloader, lives in flash memory. And in fact, as we'll see, it always lives in the first 256 bytes of flash memory. There's a bunch of different valid stage 2 bootloaders associated with each of the external memory devices with which we might be communicating, right? So there's sort of one for each. The boot ROM knows the checksums associated with each of these valid bootloaders, and so it knows when it has found one. Like with the other stuff, you can go through here and read this in detail. I'm going to just summarize and say that the stage 2 bootloader is mostly responsible for doing further configuration of the particular external flash memory device that we happen to be using. So the boot ROM could read at a low speed from any one of those external flash memory devices. The second stage bootloader, once it knows exactly which external flash memory device it's communicating with, it can go in and do the specific configurations for that particular device in order to set it up for high-speed communication. And that's most of what it's doing, is communicating directly with that external flash memory, getting that specific one set up for high-speed communication to our execute-in-place cache. I'm going to kind of gloss all over that. I guess the only thing that's perhaps interesting to point out is perhaps it stands to reason that if we go, oops, they've rearranged this. Okay, let's see if we can find it. Boot 2. We've rearranged the SDK here a little. So let's see, boot. Do I have it open already? Let's see. That's okay. What I was going to show you, which I don't really have to because perhaps it stands to reason, there's a whole bunch of different stage 2 bootloaders, one associated with each of the possible flash memory chips. Okay. What I want to actually draw our attention to, though, is though the details associated with each of those stage 2 bootloaders change because each one is communicating with a different external device, and so the specific configuration commands are a little bit different for each one. What's common among all of these stage 2 bootloaders is the exit sequence. And this is particularly interesting, particularly if you are interested in writing your own bootloader, because it reveals how we branch to our own application code. And so I want to take a moment to talk through this process in particular. So at the end of this stage 2 boot process, the following occurs. It's a very short ARM assembly program. The first thing that we do is pop a value from the stack into register R0. In the event that we have arrived at this exit process from the boot ROM, one of the last things that the boot ROM does is push a 0. Okay, so in the event that we are coming from the boot ROM, then what we will have popped into register R0 is a 0. We check that that is indeed the case by doing a comparison between the value in R0 and the value 0. And in the event that there's a match there, we fall through, or I'm sorry, we then branch if equal. So in the event that that comparison is true, if those two values are equal, the value in R0 is equal to 0, we branch to this vector in flash label. Otherwise, we interpret whatever value we popped off the stack into R0 as being a valid entry point, and we just branch to it. Okay? But generally speaking, right, if we're going through this whole boot process, we would find that we've come out of the boot ROM, we've got a 0, so we branch to vector in flash. The first thing that we do is we load register R0 with the following value. This is a macro. I'll show you what it stands in for in a moment, but it's execute in place base. That is the base of the flash memory range of addresses in the RP2040, plus an offset of hex 100, plus an offset of 256. What this address represents is the very beginning of flash memory plus an offset of 256 bytes. Remember I told you that stage 2 bootloader is exactly 256 bytes long. Some of them are different lengths, a little bit shorter. In the event that they're shorter, they're padded to be exactly 256 bytes long. So where we are going here, the address that we are specifying is the first address in flash memory after the stage 2 bootloader. That is what the address in R0 now represents. We then load register R1 with a different address. It's the PPB base. This is the sort of the base of the collection of registers associated with the ARM processors, plus an offset that is M0 plus VTOR offset. This is, let me just pull up the data sheet. This is the address of the following register. Let's just see. It's going to be in here, presumably. VTOR, the vector table offset register. As we can see, this register indicates the address of the vector table. The vector table being the collection of addresses associated with our interrupt service routines. And by ARM convention, the top of our vector table holds the stack pointer. Then we have the reset address, the reset handler address, and we have our vectors, right? So this VTOR register holds that address. And so if we pop back to that exit from boot sequence, what we now have is register R0 holds the first place in flash memory above the stage 2 bootloader. Register R1 holds the address of the VTOR register. We then say, please store the value held by register R0 to the memory address pointed to by R1. So what we are in effect doing is writing the VTOR register with the address, the data held by R0, which is in fact that first address right after the stage 2 bootloader. That's where the vector table lives. And we'll see in a moment how we know that's where the vector table lives. As it turns out, we know that's where it lives because that's where we've said it should live in the linker script. We're going to look at that in just a moment. But we have said, put the vector table right after the stage 2 bootloader, and so that's where we know that we'll find it. Okay. What we then do, the next command here says, please load the value from the memory address pointed to by R1 into register R0, then increment by 1 and load the data of the next address into R1. So what this implies, given what we just said, is what R0 now contains is the data that was pointed to by R0. R0 was pointing to the top of that vector table. The first element in that vector table, by ARM convention, is the stack pointer. So what we now have in R0 is the stack pointer value. We then incremented. The next value in the vector table by ARM convention is going to be a pointer to the reset handler, a function that we're going to take a look at. The address of that reset handler now lives in R1. The penultimate command there, MSR MSP R0, what that says is, please set the main stack pointer to the value held in R0. That's us setting the stack pointer value. And then BX is branch to R1, branch to the reset handler. So in a subsequent lecture, we're going to look at writing our own custom bootloader. And that is a particularly informative part of this boot process to understand if you're writing your own custom boot handler. This is how we set the stack pointer. This is how we branch to some, function. Any questions about that? So what's this reset handler doing? Well, what the reset handler is really responsible for, so when we have flash memory and we have RAM, right? The flash memory is non-volatile, and when we program the RP2040 with a new program, what we're doing is writing to that flash memory. And then you all are aware that you can power off the RP2040 and power it back on, and the program that you loaded last time just boots right up and starts running, right? But that program makes use of RAM, which is non-volatile. Every time you power off the system, you lose anything that was stored in RAM. So it must be the case, and furthermore, your program is making use of that RAM in some ways that require initialization. For instance, it might be the case that your program initializes some variables that it then uses. Int x equals 5. Well, if your program is modifying the value of x at runtime, x has to live in RAM, but it needs to be initialized with this value of 5 before the program actually starts. And so it's the responsibility of the reset handler, in short, I should say, it's the responsibility of the reset handler to go through and initialize RAM before our code actually starts executing. It gets RAM ready to go so that when our code starts, it's configured as it should be. Talking about this in detail requires that we take just a very brief tangent on these linker scripts that I alluded to. So what to say about this? So we're going to look at a linker script in just a moment, but let me just say first of all, kind of in the abstract. When you compile your program, it compiles to a collection of machine executable code, but after having passed through the compiler, those machine executable programs, they don't know what microcontroller they're running on. They don't know what device they're running on. they don't have any associated place in memory where they're supposed to go, right? They are just compiled programs. It's our responsibility to take all of the compiler output and organize it according to the memory layout of the particular microcontroller that we are trying to program. That organization occurs in the linker script. This is where we take the device-agnostic output of a compiler and organize all of those outputs into a layout that is in agreement with the data sheet of the actual device that we're trying to program. And the output of this compiler it generates files of a few different varieties. It'll generate text files, .text. These represent executable code. So perhaps it stands to reason that, generally speaking, in our case, that executable code will go into flash memory, though some of you may be aware that if you change your CMake configurations a little bit, you can actually tell the system, I would like for you to move this into RAM for faster execution. But generally speaking, our code goes into flash memory. There's a section called data that contains our initialized data, int x equals 5, right? Our initialized variables. Those would get consolidated into a collection of compiler output objects labeled data. Those are ultimately going to end up in RAM. It's the responsibility of the reset handler to put them there at the right place in accordance with the linker script. There's a BSS section. This contains uninitialized variables. We're going to initialize them all to 0. The linker script will be responsible for doing this, but okay, that's another one of its responsibilities. And there's also a const section. I have mentioned in previous lectures that if you have, let's say some big audio file, background music for your video game, that you want to have a DMA channel constantly be putting out, if you know that you aren't going to be modifying that audio file at runtime, it's a good idea to label that big character array that represents the background music that you're going to be playing as const. And what that tells the compiler is, my application code is not going to modify this at runtime, and so you are free to put this into flash memory as opposed to putting it into RAM. And so there's a section of compiler output stuff here called const that goes into flash memory. The linker script takes all of the compiler output of these various flavors and organizes them in agreement with our particular memory layout. So if we take a look at the default linker script for the RP2040, which I have here, what we'll see at the top is a section labeled memory that gives names to some memory addresses that we pulled out of the data sheet for the RP2040. In particular, it specifies that the base address of flash memory is at hex 100, etc. This comes from the data sheet, which we could look at if we cared to, but if you go to the data sheet and you go to the memory layout section, you'll see flash memory associated with this address of this length, 2048K kilobytes, I believe. RAM, we're saying that begins at hex 20000. It is of length 256 kilobytes. And then there's a scratch X section and a scratch Y section. What we'll see is that the rest of this linker script that organizes all the compiler outputted stuff into memory uses these as references. So when we say, please put this into flash, it now knows that flash lives at that address. So let's just go through a little bit of this. The next section here of this linker script that we see after memory is sections. This is where we are actually organizing the compiler output into our microcontroller memory. You can say that we declare a first section here called flash begin. This does not actually add anything to our to memory just yet. We're just giving ourselves we're declaring sort of a variable here that represents that flash binary start will be made available to our program. We can observe that from our program. This represents the flash binary start address. Since this is we haven't put anything in flash yet, what we should expect to find there, we can see this in just a moment, what we'll expect to find there is this address. What then happens is every time that we add something to, say, flash memory, it'll put that stuff in flash memory, and the next thing that we add gets added immediately after it. So we're filling it up from the bottom. what you'll notice is the first thing that we add to flash memory is everything that has the extension .boot2. This is the stage 2 bootloader. It has been designed to take exactly 256 bytes. It's the first thing that we put into flash memory, so it lives right at the bottom of flash memory. This is how the Bootrom knows that if it reads the first 256 bytes of flash, it should expect to find the stage 2 bootloader there. The next thing that we add to flash, by the way, we check for that here, notice. The little dot here means please give me the current address, right? So we're getting the boot2 start address before having added the stage 2 bootloader to flash memory here, and then we get the address at the end, and we're checking there in line 51. We're just making sure that better be 256 bytes long. If it's not, stop this because something's wrong. So we're checking to make absolutely certain that that's 256 bytes long. Then we go through and we start adding our actual program to flash memory. You can see that we get the logical binary start here. So what we should expect to see, what we will see when we actually go look at the compiler output here in a moment, is that that is going to be at an offset of 256 bytes from the base address of flash. The first thing that we add is .vectors. That's the vector table. Stack pointer, reset handler, then all of our vectors. That's what we'll expect to see. There's something here called the binary info header. It contains information about the rest of the program. Here's our reset handler, our constructors, our destructors, etc. All of that goes into flash memory. Let me just see here. I want to jump ahead to, let's jump ahead to the data section. Remember that data contains initialized variables. We want these to go in RAM. So this describes all of the stuff that the reset handler is going to put into RAM. I'll note just first of all, because it's kind of interesting to note, the first thing that we put in RAM is a copy of the vector table. At runtime, it's kind of handy to not have to go into external flash memory every time we need to access that vector table. Let's just put a copy of it right at the top of RAM. Then we don't have to go outside and do all these transactions every time we have to hit the vector table, because we expect to hit it a lot and asynchronously, right? So it's nice to have it in RAM. Okay, then we go through and we add everything here labeled data. This is all of our initialized variables, okay? And so on and so on and so on. The point I'm trying to make here, we don't need to go through this in excruciating detail, but what I'm trying to make is what the role of this file here is to take all of the agnostic stuff coming out of the compiler and organize it according to how we would like it laid out in the actual memory of our device, which we specify up here and which comes from the data sheet for this device that we're actually programming. Let's say you were writing a stage 3 bootloader and you wanted to compile a program such that it would be loaded not right after the stage 2 bootloader, right? You can see that right now, right, by default, our program, which starts with the vector table and then has, everything else, is loaded right after the stage 2 bootloader. So that is to say it's at the base address of flash memory plus an offset of 256. Let's say you wanted to put a stage 3 bootloader after the stage 2 bootloader to do something fancy. I don't know, maybe it looks for data from some other kind of sensor, a serial input, Wi-Fi, whatever, right? You want to put a stage 3 bootloader there. But you want to compile a program for compatibility with that stage 3 bootloader. One thing you could do is change the linker script for the application code that you're compiling to be loaded with that stage 3 bootloader such that its base address for flash puts it above that bootloader. Right, so you have the freedom here to decide where this stuff goes. And just by the way, if we take a look at the actual output here, among the various files that the compiler generates is always a map file. This describes the actual memory layout that it has used the linker script to put together. And if we scroll around, this is just for Blinky. But what we will find is there's our flash begin label, exactly where we should expect it, right at the base address of flash memory. You will see the the stage 2 bootloader starts at the base address of flash memory, extends how far? To an offset of hex 100. That's 256 bytes. That's where boot to end is. It's exactly where we expect to find it. Immediately after that, and in accordance with the linker script that we were just looking at, we then find our text section. Here's that logical binary start label. And then you'll remember that the first thing that we loaded into flash memory after the bootloader was the vector table. And here's that vector table. Okay, there's that vector table. So the job of the reset handler, it has a few jobs, but one of the jobs of the reset handler is, let me see, what do I want to show you here as I talk about this? One of the jobs of the reset handler, when we program the chip, we're only programming flash. So the reset handler has to take stuff, initialized variables, for instance, that we have put into flash and move it to the correct place in RAM. So one of the jobs of the reset handler is to go through and using some of those labels that we were looking at, logical binary, start, and other ones, it knows where it needs to go into flash memory to find the stuff that it has to copy over into RAM. And the other thing that the linker script is telling it, by way, again, of these labels, is where in RAM it should be putting these things. So for instance, this data start equals dot, right? Because we've specified that this should be loaded into RAM, actually RAM at flash, that means it's going to go into flash, then we'll load it into RAM. But these labels here specify RAM addresses, which is different from the load address here, the load address of the .data section. This is where this section lives in flash. That's where when we program the device, this is where it lands. E-text, that's where the end of the text section, that's where this lives in flash memory. Those labels there, data end and data begin up above, those specify the destination addresses where this should go in RAM. So our reset handler is going to use those in order to make that happen. So we can go look at the reset handler. Let's see. I think I have it open here. Here's a reset handler. Reset. Let's talk through it over here, though. I have it sort of summarized. First thing the reset handler does is make sure that it's CPU 0. It should be CPU 0 because we've already checked this, but there's a redundant check here. Okay. By reading the CPU ID register, it's a defensive maneuver as I have specified here. In the event that it finds that it is in fact core 0, what it then does is perform a data copy. It goes to the section of flash memory that holds the data output, the initialized variables output files from the compiler, and moves them to the correct place in RAM. And it does so by way of this table that we've constructed here. Remember, e-text here, we were just looking at this in the linker script. This represents the load address of the data section in flash. Data start represents the start address for that section in RAM. Data end represents the end of that section in RAM. There's a really simple loop here in the reset handler, and then similar for these other two sections, for the scratch X and the scratch Y sections as well. This whole table terminates with 0 so that we know when we've found at the end of it. But then all that this reset handler does is, by way of really a rather simple collection of assembly code here, it goes through and just starts copying from the load address of, say, the data section to the start address of that section in RAM. And it keeps doing so, incrementing the address each time until that address has incremented to the point that it matches the end delimiter of that section. Once it's found the end delimiter of that section, it moves to the next section, copies that over, then it moves to the next section, copies that over, and ultimately it will find that 0 that represents the end of that table. At that point, it has copied over the data section, the scratch X section, and the scratch Y section. Its next responsibility is to 0 all of the RAM associated with uninitialized variables, the BSS section. It accomplishes that here, right? So it loads the value of R1 with the start address in RAM of the BSS section, of R2 with the end address. And then by way of this rather simple loop, it just loops from R1 up to R2, zeroing each address as it goes. So it zeroes out the whole BSS section. After having done all of that, it does the following. Okay, so after having initialized the data section, the scratch X section, the scratch Y section, and the BSS section, it falls through to a platform label called platform entry. This is all within the reset handler. What this does is it loads register R1 with the address of a function called runtime init. We then use a branch and link instruction to R1. What that means is please branch to that address, execute the function that you find there, and when you're done, come back. Come back to this line. So this is going to go execute the runtime init function, which we could go look at. And if we were to go look at it, what we would find is basically it's setting up the clocks, setting up more peripherals, doing more setup for us. Comes back, we hit another function, load register R1 with the address of a function called main. That's your main. Branch and link to R1, so this branches to main in your function. In the event your main exited, it would come back here. Your main, of course, never exits. So it is that line right there, BLX R1, that's where we enter your program. So this whole sequence, the data sheet describes this whole process into what it calls the hardware-controlled boot process and the processor-controlled boot process. This whole process starts in hardware. We turn on the ring oscillator just by applying power. That ring oscillator is just a ring of inverters. Click, 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 right? A ring of inverters. We clock the system off of that ring oscillator and turn on the bare minimum number of peripherals that we need in order to do the rest of the process that we just described. What do we need in order to do this? Well, we need the bus fabric. We need to turn on ROM. We need to turn on SRAM. We need to turn on the execute in place memory. We need to turn on the processor complex and some voltage regulators. Okay, we turn on all the stuff that we need to turn on. And then the first software that begins executing is the Bootrom. The Bootrom lives on chip. Its job, in short, its job is to figure out which flash memory device am I communicating with. I'm compatible with a bunch of them. They all have slightly different interfaces. I need to figure out which one I'm talking to. And furthermore, is there even a valid program in this? The way that it does that is it reads out the first 256 bytes from flash memory over sort of a standard SPI channel, reads that into flash, computes a checksum against it, and asks whether that checksum matches one of the number of checksums that it knows represents valid boot to programs. In the event that it finds one, it branches to it. In the event that it doesn't, it goes into USB boot mode. The stage 2 bootloader, it knows which external flash memory device it's associated with. So it's responsible for going through and actually doing the specific configurations for that particular device to set it up for high-speed communication. It goes through and does all of that. And then it executes its exit from boot stage 2. When it exits from boot stage 2, what it does is it sets the stack pointer. It sets the VTOR register for the ARM processors to be the address of the vector table. And then it branches to the reset handler. The reset handler's job is it goes through and it takes all the stuff that was loaded into flash, because that's what we program. We program the flash. Takes all the stuff that was loaded into flash memory. It uses some of these program labels. I'm not sure that's the vocabulary I'm using. The labels from the linker script that delimit, here's where this starts, here's where this ends, so that it can go through and copy the sections of flash memory that it needs to over to RAM. The stuff that our program assumes is initialized, it goes through and actually initializes. It gets RAM set up for us. And then the last thing that it does, right, it goes through, copies over the data section, the scratch X section, the scratch Y section, it zeroes out the BSS section. And then finally, it branches in links to runtime init. You could go look at this. This is doing the low-level initializations of clocks, etc. Comes back, branches to main. And then your code takes over. So my thought is that perhaps next time we'll talk about how we might take this and tweak it so that we could add a third stage bootloader, one that lives after boot stage 2, that does something fancy, something kind of custom. We'll talk about that next time. Okay, see you all I'll see many of you in lab this afternoon. I'll see the rest of you on Wednesday, if not before.